Welcome to the last of our webinar series. We're going to round out our virtual workshop that we did this year with an interesting topic, one that kind of brings a lot of things together in one project. We usually like to talk about a few projects, not just talk about how to do concrete, but show some examples of how others in the industry are using concrete to their advantage. And in this case, we think we have a project that does that. So welcome. Hopefully everybody is excited to wrap this up. But we know people are getting busy, getting back to work. Weather's getting nice. So our attendance has been declining since our peak in February. So we know it is time to wrap it up. So this will be the last in our series until probably the fall. We'll do some webinars and we'll discuss whether we're going to do an in-person workshop next year or not. I'm Steve Walkus. Again, those of you that have tuned into some of these, Director of Engineering, West Michigan for MCA. We're glad you guys are all on the call this morning. We're going to go about an hour, probably less than an hour, but we're going to hopefully have some questions, and we'll stop the speaker. If you do type some questions, please use that Q&A button in the Zoom software there in your control panel. Type in your question, hit send, and we'll pause the presentation and ask that question and have some discussion. So that's the main way to interact with our speaker this morning. There's a chat window as well if you just have a quick comment or wanted to share something with myself or with our speaker this morning. And then I will send out continuing education certificates possibly later this afternoon or tomorrow, based on those of you that are logged in this morning. Big thanks to our three companies that have sponsored this entire series: Superior Materials, Levy Company, and St. Mary's Cement. They ponied up and sponsored the entire workshop this year. There were some other individual sponsors as well for individual topics, but big thanks to those companies, as well as to our speaker this morning, Mr. Doug Wittler with Premiere Concrete Admixtures and Concure Technologies. He co-founded Premiere in 2005, and he is the company's and Concure Technologies president and CEO, both companies, sister companies. Doug began his career as a concrete technician for Toledo Testing in 1985, so he does have a very significant testing background. Started working for an admixture company in 1988, which eventually became Axim, which then, since left Michigan as far as producing admixtures in our state, at which point he started Premiere, like I said, in 2005. He has been active with our association for a number of years, has served on our board of directors, is a big supporter of MCA, so we thank him for that. He's been involved with ACI as well, American Concrete Institute, the 332 committee, and various other committees. And Doug has his education from the University of Toledo, including his latest degree, or his last one was an MBA. So that's Doug's background, a little bit about him. I'm going to let him take over sharing, and he's going to talk to us about how his 35 years of experience and knowledge was brought together in kind of a pet project of his, bringing concrete to the forefront and using concrete to his advantage for this particular project. So Doug, I think we're seeing your screen, so please feel free to take it away.
Okay, thanks, Steve. I appreciate it. I also appreciate the invitation from the Michigan Concrete Association to talk about this building. It was kind of interesting. I started this building back in November, and I've been planning it for about 10 years. We have a home on the lake and needed a place for boat storage and lawnmowers and all that good stuff, and had them scattered all over God's creation. So, but in thinking about the building, the longer time went by, if you're in the concrete industry, which all of us are, you start thinking about, okay, how can I do some of this interesting concrete stuff? So what I tried to do was I tried to make a building with as much concrete / cement as I possibly could. So that was the purpose of it. There were a few considerations that we needed to do in regards to the building. one thing I want you to notice is that with the footprint of this building, we had a fairly large hill right here and wasn't much use for the property. So we kind of wondered, well, could we dig the building into the hill and have it there? So that's kind of what we decided to do. I had a neighbor up in this area that really didn't want to stare at a major building. They didn't want their view of the lake to be obstructed. So we kind of talked with each other, figured we put this in the ground, and really right now from their view, all they can see is a little bit of the roof, which worked out pretty well. But we moved an enormous amount of earth out of here. Um, you can see that really from the first slide I have. It took quite a while. We broke ground, I think, in like the third week of November. So this was going to be a wintertime project right from the get-go. There's our lake house right now across the road. We're planning on doing an expansion there here. And based on the results of the ICF and things that we did on this side of the road, I'm very, very seriously thinking about incorporating all that over here. Now it is a log home, so one of the things we got to I'll talk about at the end of the presentation is how I can tie that all in. But when we started the project, there's a few things that we wanted to accomplish throughout it. And this is just an overview, starting with the research and development of an extended pot life polycarboxylate. Now that's directly related to our business. As Steve said, I'm the president and CEO of Premiere Concrete Admixtures. And when you're doing R&D work for admixtures, you can do all you want in the lab with mortars, and then moving on, once you develop your products for mortars, you move on into concrete and you do your testing in the concrete lab, and things can go wonderful. But until you get those products into actual field concrete, mixing them up in a truck, going through the batch plant and everything else, sometimes it doesn't work out the same. So a good research and development system has to go all the way from mortar into concrete lab out in the field. Well, there's pros and cons to that. You tend to get some free concrete once in a while, but you never know what you're going to get. So there's been times where testing didn't go as well as we'd hoped, but you know what? That's why I'm a big fan of exposed aggregate. If something goes wrong, some of those sins can be hidden. But pros and cons to being able to do test concrete on the job. Even with this job, there was some great stuff and there was some so-so stuff. So we were going to do the research and development on extending the pot life of polycarboxylates, which is important. Polycarboxylates have been around for a long, long time. In the US, they've been here probably about, I'm going to say about 20 years. Prior to that, they were invented over in Japan, and they've been there for probably as long as 30. And we've all worked with them, but there's two areas of that chemical that can be a little challenging. One is pot life, and the other one is air entrainment. Almost all polycarboxylates make air entrainment very, very sensitive. So one of the things that we're trying to do is we're trying to develop a product where we can use a higher dosage of air to make it more controllable when you're using the product. A lot of times right now, polycarboxylates are usually using anywhere from, they're as low as 0.1 to 0.2 ounces per hundredweight. But for accuracy of dosing at the batch plant, it's better if we can get that up to 0.3, 0.4, 0.5 ounces a hundredweight. It's just going to make things more consistent down the line. In addition to that, we wanted to work with ICF, Insulated Concrete Forms, something we all talk about, very, very interesting. As I was going through the project, I kind of fell into that, but very glad I did. We also wanted to take advantage of this project in order to do some additional research on concrete temperature monitoring and concrete match curing technologies. From a technical standpoint in this presentation, that is probably going to be what I would hope to be the most fascinating part of the presentation from a technical standpoint. It's just truly incredible stuff. I hope to see the concrete industry implement this more and more as time goes by. The more it's implemented, the better the technology you'll get. And as a lot of things out there, if we keep working on it, it can become a very easy thing to utilize. After that, we're looking at jointless radiant heat in a concrete floor. Now, by jointless, I've always been curious on doing a floor without any construction joints in it or control joints. Um, Part of the reason I wanted that was because we were going to do radiant heat, and in addition to that, we were going to put epoxy on the floor. Now, I could have left it a nice concrete floor, but I've always kind of wanted to throw a texture on it, and experiment with epoxy and stains and things like that, more concrete experiments. But if you joint the floor, those joints have to be filled in. And sometimes if you're doing an epoxy treatment or staining and stuff like that, it's not going to look as good. You're setting yourself back and you're creating more challenges than you need. So we wanted to go with structural fibers inside the floor, and we ended up going with a fairly high dosage. Usually on a jointless floor, structural fibers can go anywhere from 3 pounds a yard up to as much as 9 pounds per yard, depending on the structure. For our floor, I wanted to get a little bit on the high side, so I went with 5 pounds per cubic yard of structural fibers, mainly because I wanted to see how it worked, how it finished, etc. Exterior considerations, just keeping in the theme of cement-based products. We're going to go with cultured stone, and we are thinking about going with precast concrete logs. That's another interesting thing too. And I was talking to Steve yesterday. I actually picked up a place off one of their email blasts that went to a company in Kentucky called, I think, Old Kentucky Log Homes. If you ever want to look it up, they make precast out of lightweight concrete, precast logs. The only difference between those than what I have over here on the log home is this is a D log. So it's got kind of it's got a rounded end on the outside, and there's no chinking here. It's tongue and groove. If you go with the precast concrete logs, it's more flat, looks more like a timber. And in between, there's mortar, which replicates chinking. So I just didn't know. I kind of wanted the buildings to tie in together, and that's the only thing that's kind of keeping me from going both feet into the precast logs. In addition, although I am not a green freak, I do try to do as many green applications as I can. Solar energy, I'm a big believer in it. I'm actually going to be getting my first electric truck this year. So we wanted to incorporate that into the building too. So with the overview done, let's just dive right into it. When you're looking at footers, footers are a great place to test concrete. You don't need a lot of strength. They're very forgiving. If you have to add water to be able to get the stuff in, no problem. It's just a great place to take advantage of doing a preliminary run on what you want to achieve down the line. So when we decided to do that, we picked the same mix that we were going to run with throughout the entire project. The only difference between the mix in the footer, the wall, and the floor, the interior floor, is that the footer and the wall contains natural stone. The floor, the inside floor, the interior floor consists of crushed limestone. I did that just because I wanted to try to get the most durable floor I could on the inside because of the epoxy coating and because we weren't going to be sawing it in any way. So when we started the pour, we went with a standard mix, which I'll outline here, I think a couple more slides in, 564 pounds of cement and et cetera, but I'll get to that soon. We wanted to look and see how the concrete performed versus its pot life, as I said earlier on. We wanted to check out the air consistency. If we had to retemper, we wanted to establish some retempering guidelines so that when we got to the wall, we weren't going to overshoot any slumps. The wall mix was used in the footers, as I said, but the other thing that we did, which was important, is when we did the footer mix, we wanted to establish a maturity curve. Since the mix was the same as we were going to use in the wall, we decided to stop off at our manufacturing facility, which is located about 15 minutes from the project site. So the batch plant we used was in Bryan, Ohio, Paul's Ready Mix, and they had a 20-minute haul, about a 25-minute haul up to our plant, and then they had an additional 15-minute haul over to the job site. So by the time the concrete got to us, we were looking at about 50, 55 minutes in the age from initial batching. But the reason we wanted to do that is because we had all the equipment right there at the plant. It was much easier for us to establish the curve. Now, when we did the curve, we dropped off enough concrete to be able to do. I think we make about 16 cylinders when we do a curve. And the main thing you want to look for on breaks with the curve is usually early age. That's the biggest difference between concrete that's put in a cure box, et cetera, is knowing the accuracy of your 1-day break, your 3-day breaks, et cetera. And the reason you want to know that is because that's usually when decisions are made regarding the stripping of a wall, the recycling of forms, whether someone can release a tendon, in pre-stress situations. Those early strengths are critical. And to rely on a cylinder all the time, depending on how that cylinder is cured, is usually fairly inaccurate. So we took the concrete, and when we make the curve or when we make the concrete, the maturity considerations that you want to do is that you always want to be conservative. And how are you conservative? When you make that concrete into your cylinders, you want to try to get the highest allowable air content and the highest allowable water cement ratio. And the reason you want to do that is you want to make the concrete as weak as you can while still meeting specifications. That way your breaks and your estimates on your maturity will generally be lower than what it is in the actual piece that you're trying to gauge. In maturity, it's always best to try to be on the conservative side. And that's one way to do it, is by, when you're making the curve, is to make that concrete just as weak as possible. So we made the curve, and the other consideration you want to have when you're making a maturity curve is you want to pick a temperature that is going to be somewhat similar to what you think you're going to achieve with the concrete in the pour itself. We were in the middle of winter. This concrete was going to be poured in the first week of December. Really didn't know what we were going to get, but we thought because we had insulated forms, we were at least going to be, 73 degrees. So we chose a specified temperature of 73 degrees. We put the cylinders, I'll have a picture coming up, into our TruMatch box, which maintains a constant temperature in a water bath. And then we broke the cylinders accordingly. When we decided to break those cylinders, you'll see right here that the first one was broken. It was just about 19 hours, another one at 25 hours, another one at 50 hours, and then so forth and whatnot. Now, you can actually terminate a maturity test after about 7 days of establishing a curve, because the information at that point in time will be fairly accurate going all the way out to 28 days. You can break one at 28 days if you so choose, but you don't have to if you don't want to. So the results of these breaks ended up on the curve here, seeing where we had 30-30 on the first break. The second break, we had 34-35. And then the third break, we had 4,980. And then, although you can't see it on the screen, the next break was up around 5,800 PSI, well over the design strength of any wall. So we were okay with this. We were good to go with the curve as it is. To give you some dimensions and some considerations on what we had with the wall, we'll start here by telling you that the width of the project was 48 feet wide. And why did I pick 48 feet wide? We did that because of the trusses. We were putting attic trusses on top of the building, and that was the longest span we could have without having to bring the trusses in pieces and reassemble them on the site. It was also a trucking issue as well. So 48 feet was the longest continuous span I could get on a truck. So that's what I settled up on. The length of the building is 80 feet long. The reason that we settled in on 80 feet is once we had our setbacks on the property lines, et cetera, That's about as long as I could make it. The ICF forms came from a company called Nudura. I know there's plenty of other options out there. And honestly, the reason I settled on Nudura is because my basement contractor, or the contractor, was familiar with it and had done jobs with it in the past. Uh, this project came together fairly quickly. So I changed my mind a couple times. I was going back and forth. And at the end, it was easier just to run with what he said. But I will say that that was a good choice anyway, because I'm very ecstatic with the performance of the product. Um, I like how they go together. I like the rebar systems. Everything was really cool. The other nice thing about Nudura is since I'm building this in Michigan, I elected to be my own general contractor. So I'm pulling my own permits. And Nudura had engineering stamps, which I had to have for my plans to be approved by the local building inspectors. So the design, most of the spacing of the rebar and everything came from Nudura. So I didn't have any problem pulling permits. When we're talking about design from Nudura, one of the things that we ended up doing is they gave us the spacing factors and the size of the rebar for the project. It's a little diagram here that kind of shows you the configuration, but basically we went with 18-inch on center number 4s for the horizontal rebar and 16-inch on center number 5s for the vertical. That is fairly close of a representation on how it looked. The other thing we had to consider is the height of the wall. I wanted to go as high as I could. 12 foot was as high as I could go with the pre-approved engineering stamps. So we went with 12-foot ceilings. And then because the span is 80 feet long, anything over 60 feet is required to have a dead man in it. So and there'll be a picture coming up shows it a little bit better, but we put a dead man and attached it into the wall right here in the center, going 6 feet out and 6 feet up. The reason that we had to have the rebar configuration the way it was, one of the major considerations was backfill height. And you can tell down here, we dug down, we had 10 feet of fill on the north side of this wall. So that dictated the rebar configuration. In addition, because of the span and everything else, we had to go with a 10-inch wall. And the supports that my contractor went with was 4 inches, or not 4 inches, 4 feet. Sorry about that. 4 feet. The type of the insulation with the Nudura forms is a 2 5/8 inch thickness of closed cell insulation type 2 on both sides. And the R value, and I did find this a little interesting. I thought, you're putting it into the side of a hill. I kind of thought that the R value would be pretty good up against the earth, but it turns out that it's not. The R value of a buried wall is going to reach a value of around 30. But once you get out here to more exposed areas, it actually increases to 40 to 50. One of the things I wanted to say in the beginning too is please, if you have any questions, go ahead, fire them off to Steve. It's always good for me as a presenter to be answering them as the presentation goes on. You don't have to wait until the end, but feel free to do that. Once the walls were up, we got on to our next phase of the project where we wanted to do some temperature monitoring, and also while doing the temperature monitoring, incorporate maturity estimations and match curing. This is a piece of the vertical rebar. We ended up tying 3 temperature sensors right onto the rebar itself, one right here, one here, and one here. So that when it was lowered into the wall, we ended up with final locations at about a foot above or below the top of the wall, in the center of the wall, and again to about a foot below the end of the wall, or above the end of the wall. We were kind of curious because I really didn't know what the heat would be in these areas. I had originally expected this top level to not be as warm as the rest of the concrete, mainly because this was an open top. This top was left wide open after the concrete was filled. we got a little bit of an amazing, well, not amazing, but interesting results from it. And actually, I don't think I have a slide of it, so I'll just tell you now. The coolest part of this pour actually ended up down here on the bottom. And it was at times 10 degrees cooler than everything else. The only thing I can attribute it to is that it was sucking the heat out into the ground. Of course, the heat, now that I think about it, rises up throughout the wall. We were always about 15 degrees hotter in the center of the piece, but up here we actually kept more of more heat than what we did down here. It did not escape out the top near as much as it did on the bottom. So after we placed those sensors in there, we ended up hooking up our control box, which cellularly sends all the data to the cloud and then into the server, to where it interprets that data and then comes out with the information that we need. The day of the pour, we placed it in 4-foot lifts. Now, I was kind of surprised by that, because I had always heard that when you're dealing with insulated concrete forms, everybody's really concerned about blowouts all the time. So I was concerned about blowouts. We had 80 cubic yards to do. With a 4-inch lift, I didn't know what kind of slump would be acceptable, or 4-foot lift. I didn't know what kind of slump would be acceptable. I kind of thought we were going to be around a 4-inch. But in talking to Endura and talking to our contractors, you know, we can get away with a little bit more than that. So we were hoping for around 7 inches. That was our goal, 7 to 7.5 inch slump. The mix design that I started to allude to earlier was straight 6-bag, 564 pounds of cement, 0.50 water cement ratio. We were shooting for 5 to 6% air, and we were shooting for that 7 to 7.5 inch slump. Again, we were going to check for air consistency and retempering. One thing off the bat I can tell you about retempering with a polycarboxylate admixture in the mix is that the old rule of thumb before polycarboxylates is that for every gallon of water you add to a truck or a yard, every gallon per yard, you'll increase the slump by 1 inch. That is not the case with polycarboxylate loads. Polycarboxylate, you have to cut that old rule of thumb in half. It's every half gallon per yard will raise it 1 inch. And depending on how much polycarboxylate's in the load, it could even be less than that. So you have to be careful when you're retempering with water, because if you put too much in, you'll overshoot your slump drastically. So it's something to keep in mind.
Doug, I got a question for you.
Yeah.
You alluded to the polycarboxylates. That's a general type of chemical, a class of chemicals. What specific polycarboxylate admixtures were used in this one? Now, you don't have to get trade names. Did you use water reducers, air, viscosity modifiers? Just tell me the types of polycarboxylates.
Polycarboxylates, and if you're ever interested, if you have a job, you can go to the data sheets and you can generally, of the product, and it'll generally tell you what it is. But polycarboxylates in general are classified as high range water reducers, but they're also very capable of being a multi-range water reducer. You can use them as a low range, a mid-range, and a high range. Now, the characteristics of a polycarboxylates are very specific. They are very, very strong water reducers. They tend to keep the concrete in a very cohesive nature. All right, they flow very well. They don't segregate. They actually have a cohesive nature to them in and of themselves. Now, you talk about viscosity modifiers. Our company elects, we have them, but we don't like to use them, because most concrete the viscosity can be designed. And like I said, the nature of the polycarboxylate will make them cohesive. In this instance, since we were looking at a 7 to 7.5 inch slump, we were really using the product more as a mid-range water reducer as opposed to a high range. You cannot beat these products for strength gain. You can have, a lot of times you'll think, okay, if I keep my water cement ratio the same, and I use like an older super plasticizer, meaning a melamine or an ethylene, that type of technology. If you run a mix head to head and you get the same slump and you use as much chemical, say a 0.50 water cement ratio, and you cast cylinders, you add the product, and let's say you get an 8-inch slump, you cast cylinders side by side, I'll guarantee you that polycarboxylate set of cylinders will break as much as 1,000 psi higher. Definitely 600, 700, but as much as 1,000 psi higher. So, the sacrifices that you make with the product and finishability, they don't finish near as well. But sometimes it's not that big of a deal. Your timing on finishing is a little different with polycarboxylates. But boy, I'll tell you what, for the strength gain that you get out of it, pretty hard to ignore them. So in what we were trying to do with the research and development here was trying to take potentially like a polycarboxylate into more normal pouring situations. Polycarboxylates are used all the time you have to use them for self-consolidating concrete. Because of the cohesive nature and the water reduction of the product, those are the chemicals you need to use in self-consolidating concrete. But we want to try to expand the use of polys into other types of applications, such as this wall. So to do that, when you get into some residential and light commercial applications, you want to try to be able to solve the issue of a longer pot life. Sometimes with SCC, depending on the type of poly, you may only get 30 minutes worth of pot life. Well, that's not a lot of time once you're batch. For instance, we batched at the plant. I didn't even see this concrete till it was 45 minutes old. If it was with the older technology, the polycarboxylates, we wouldn't have had any slump. 0.50 water cement ratio, we'd have been staring at probably a 2.5, 3-inch slump. So that's why we're doing what we're doing. Steve, thanks for interrupting me. It's a good question. They're normally high range water reducers, can be used as multi-range. In this instance, it's a mid-range. So that being said, some of the results of the testing that we got on the job is that we were very happy, very consistent. We had 7-inch slump, an 8-inch slump, 7.5, and 7. So we ranged from 7 to 8 inches. This we were very, very tickled with, 5.4% air. And I believe that was with a dosage of 0.5 ounces a hundredweight. So to be able to dose air entrainment in a poly load and obtain 5.4 airs, we're happy, because normally speaking, when you're dealing with a polycarboxylate, if you just put in 0.2 ounces a hundredweight, you're usually fighting to keep the air down. You're normally in that 7 to 8, 8.5 range. So this was something that we were pretty happy with. Already talked about the concrete being 48 or 45 minutes old. Ambient or mixed temperatures, I would have liked to see them a little higher, but that's what they came in at, 55, 56 degrees. And we didn't, even though I did figure out the retempering dosage, we did not have to retemper on this part of the wall. Another thing I wanted to let you know is that we did pump all this concrete. So, and I'm very glad we did. It worked out really well. This is a picture of the windowsill, and it's something I just wanted to comment on. It's not, you could, if this was self-consolidating concrete in this part of the form, you really wouldn't have had to cut these notches out. But to be comfortable for everybody else on site, they kind of wanted to put a couple holes in the sill plate, and they wanted to watch the concrete flow. In addition, you can see over here, they did throw an internal vibrator in, and just to make sure that there was no voids left in it. This is a picture of the TruMatch box. And as I said earlier, when we made our curve, okay, this is one of the units where we put the cylinders in when we were doing the maturity curve, shut the lid, set the thermostat to 72 degrees, and pulled the cylinders out when we needed to break them for the curve. This picture, though, however, shows the cylinders from the actual pour itself. We did the same thing as we did on the footer mixes. We stopped off, we dropped off a sample at the plant. You can do this on site, by the way, but we dropped off a sample at the plant, made the cylinders, put it in the box. Then the node this node here that's on site was then taking all the information from the pour, from this pour, and it was sending it up to the cloud, and the cloud was sending it back to this unit. And then this unit was recording and telling this heating system, this is a heating and cooling system, it told the water where to go, how quick to heat up, so that the curve, the maturity curve that you saw before that was grafting up, this unit's telling the concrete to increase it, or not the concrete, but the water, to increase in temperature so that it makes the concrete get to where it is in the wall. And you'll see that this cylinder right here also has a temperature sensor into it. So when the cylinder reaches the temperature, when the water gets the cylinder up to the temperature, this then tells this that you're where you need to be. And then it just keeps continually adjusting. So when you look at either verifying a maturity curve or actually just wanting to see what the true strength of the concrete is in the form, this is by far the best way to do it. In addition to doing the match curing and to doing the maturity estimates, this is something I have wanted to do for a very long time. We will do more experimentation on it, but I wanted to see what different cure boxes did in relationship to the actual strength of the concrete. I've got a lot of customers out there that have gone through hell with regards to cylinder breaks on the job site. They're not accurate, especially in early ages. They closed the gap toward 28 days, but nobody had really ever told me in the 35 years I've been doing this, or I haven't seen a real good comparison on what happens when a testing company comes out or somebody makes cylinders and sticks them in a plywood box or some other kind of housing in the dead of winter. Now in the summer, I'm sure there's other effects to it, but haven't gotten that yet. But here in the dead of winter in December, we decided to do companion cylinders on all of these methods of testing. Normally, if you're out on a job site, you see a plywood box is where a lot of people will put cylinders. Some will put it in coolers that are just plain coolers. There's no heating devices in them. Some are field cured, which we did field cured cylinders on this. What we predicted they'd freeze, they froze. So you're not going to see any information on field cured cylinders because that's a total waste of time. We made this plywood box. It's something that we had used way in the past when we first started the company. But even so, this is fairly well insulated. This is closed cell insulation on the bottom of the box, on the walls of the box, and also on the top. So when you put like 6 cylinders in there, the heat from those cylinders is really not going to dissipate out of the box. So you're going to get some kind of a warming value out of it. But this is generally what you see on site. Now, there are different types of cure boxes available here, and even the box that I had showed you earlier, that also can be used as a cure box. But this one has one heating plate on it, has a min-max thermometer, and it also has a thermostat. This box right here, I think we stored the cylinders at 72 degrees. So when we got them out, we put them into the box. They didn't change temperatures until we picked them up and transported them the next day to the lab. So the things we looked at is we wanted to compare the 24-hour breaks on all these units. We wanted to check the thermal curve to make sure that was, to see where that was in relationship to the various stages in the wall. And then we wanted to see how estimating the strength went. So we get to the 24-hour breaks and the comparisons, and the actual strength of the concrete in the wall at 24 hours, based off of taking a cylinder out of the TruMatch box and breaking it, was 3,240 PSI. The projection that we made when we estimated the strength based on our maturity curve projected the strength to be 3,172 PSI for just a 2% difference. So our maturity curve was extremely accurate in predicting the actual strength of the concrete. In this instance, we were happy that we were a little lower than the actual strength because it was conservative. That does not always happen. Maturity will say as long as you're within 10%, your curve is good. We like to get a lot tighter than that. For this project, we were 2%. Now we flip over here to the insulated plywood box. 1 day break, 1,330 psi, 59% difference. And that box was not that cold, but that is how drastic of a difference you have in how representative them cylinders are to the actual strength of the concrete. We did a little better on the cure box that we had at a static temperature of 72 degrees, 2,540, but we're still at 22% off. So we basically reinforced what we thought would happen. Looking a little bit further down the line to give you comparisons. Oh, sorry about that. On the 1 day strengths, we just went over those. On the 4 day strengths, we had a difference from the actual strength on maturity of a plus 2%. At we estimated 5,090 psi. The actual is 5,090. Our curve was 4,980. I think if I got that right. And then the 3690 for the insulated plywood box. So they're starting to catch up. And then the other 72 degree box was 4280. And then as we start to get out even a little further, 7 day, they start to close the gap a little bit more. 28 day, if you notice, the actual strength of the concrete and the strength of the cylinders that were in the static temperature box were pretty close. So some engineers and would probably justify, and this is correct. I mean, if your specifications are only concerned about 28 day breaks, I guess a cylinder, as long as your cylinders are in a constant temperature and not moving all over the place, you will be fairly representative at 28 days. If, however, you have any kind of construction practices that are needed to estimate the strength of that concrete prior to 28 days, cure boxes just don't cut it. Now we'll move on to the floor here. And as I said, I wanted to do radiant heat. Very, very happy with it, by the way. You know that we had 48 by 80 feet for the flooring. We ended up having 3 heating zones, one in the garage area, which is over in here. You'll see a picture of that later. And then we also have kind of a man cave living area here where we got a kitchen here and a little living area here. And then of course we have, so there's a zone there. And then those attic trusses up here presents about 4, well, we got 4 rooms up top and a bathroom. So there's another zone there. The concrete on the floor is 5 inches thick. I asked them when we designed that, is 5 inches okay? Most floors are like 4. They said not a problem at all. The only difference is it's just going to take that much longer for the floor to warm up. But once the floor warms up, there's no big difference between an inch of depth. I said earlier on, we did go with structural fiber at 5 pounds per cubic yard. I was shocked. Didn't have any, while they were power troweling, there was no grabbing of the fibers. There was no, balling up at the surface. No real adverse effects whatsoever. I was pleasantly surprised with that. But the real good thing was there wasn't any cracks. We don't have any cracks in the floor. So knowing that you can do a span of 48 by 85 inches thick without worrying about any cracks, that was really cool. And when I did my research on this, I was wondering if we really had to reduce the water cement ratio, prevent some additional shrinking. I was concerned about that. I was concerned about the amount of stone content. Most of your standard low shrinkage mixes, you're going to beef up your core sag, you're going to minimize your cement content, you're going to minimize your water cement ratio. That's not totally necessary in practice. This was a 0.50 water cement ratio, which is still, it's not real high. But in talking to other fiber guys and other people that have done it, usually about a 564 with a 0.50 water cement ratio is a good number to start with. I talked about the attic trusses just to get off concrete for a little bit and some other interesting facts. This is that 48-foot span attic truss. Here is the space that will be available to us. The cool thing is that to the peak of the ceiling here, we're getting about 7 feet 10 inches. We're almost at 8 foot. So it provided to be really spacious up top without actually having to add another level to the building. When we backfilled the wall, we were very aggressive with Pea Stone. This is that north side where I said we had 10 feet of fill. We brought in a stone slinger, started putting in, I think this is actually number 6. We were going to go Pea Stone, but the local source of aggregate was going to give us this for the same price. So we took it. So these are number 6s. And as we filled up with the stone slinger, eventually this pile would start sloping back down, and I didn't want to pay for all the stone in that big area. So we would start to backfill dirt in the back of this to help support it out. And then once we got that level high enough, we continued on up the wall. This is a picture of the radiant heat or of the boiler, which is an on-demand unit. And I was shocked. This is a very small piece of equipment with a boiler, and this little piece of equipment right here heats the entire floor of the facility and provides all the hot water to all the bathrooms, the kitchen, and everything. I'm blown away. I was blown away. Now, one of the things I want to make a comment on here. This is a propane unit. We did put a propane tank on the other side. Now, I was going, and I am going to go with solar energy. So I was trying to do everything electric. I changed my mind at the last second because, as I said, the project came together so quickly. Some of these decisions, I didn't have a lot of time to mess around. Our electrical supply at the lake is a little questionable. We go out of power more than you would care to, sometimes for a couple days. And I wanted to get a backup generator. And most backup generators nowadays, you know, the propane is the fuel source. So I figured if I'm going to have propane out there anyway for a backup generator, I'd go ahead and I'd go with the propane unit currently. Now, as things evolve with solar energy and backup batteries and things like that, if I want to, I'll pull this unit and go with an electric boiler at that time. But right now, the difference in cost between a propane boiler and an electric boiler is probably around 10 grand. So that was another reason that I decided at the last second to switch it out. This is a picture of inside the building. As you can tell, not one, control joint in this floor. This is after we put the epoxy on it. We did put 2 trench drains in the garage in order to wash the vehicles, etc. And that's a finished look. Now I'll come back to this picture in a little bit because I want to talk about how you affix things to an ICF wall. Right here is an ICF cutout, and the reason we did this picture, number one, this is how you wire in there. You got to cut out some of the foam, and then after this wiring is done, we'll come back and we'll put some spray foam in there to clean that back up. But this little black piece that you see here and here, that's what you'd call like the stud of the forms. And if you see these squiggly lines right here, that tells you where those plastic studs run. So they're 8 inches on center. So they're 8 inches apart. And that's what you use to adhere any siding to the foam or anything you have to nail down or screw down. And I will say that these suckers, once you get into them, they're hard to penetrate. If you have a self-tapping screw, once they grab, and it'll suck that screw right in. When we did the steel siding inside of the garage area, I had a choice to make. Normally when you put up siding, you'll put your screws in every 9 inches on center. That way you never end up with a screw on the seam of the pieces. But to put furring strips on there to make that happen, that's going to leave you, the depth of the furring strip of like a cavity. So if somebody actually ended up running up against the wall or anything with any force, you dent the siding. So I made the decision not to do that, and I stuck with the 8 inches on center of the plastic studs in the forms to fasten the steel to. And the only problem with that is that it will, every once in a while, you'll end up with a mending screw that will go on the joints. So if you look down at it, it's not going to look totally perfect, but by the same token, it's a sacrifice I was willing to make, because you go up against this wall, you're not going anywhere. I mean, it's right up against the foam and the concrete, very sturdy. Some other interesting facts. I was talking about the R value of the Nudura forms. Well, this is the upstairs with the attic trusses. And what we also decided to do is we wanted to go with a tightly insulated structure. So there's no ventilation in the house. It's called an envelope insulated job, where the entire structure is completely closed off. This is 4-inch thick closed cell spray foam insulation. I'll see how it goes. Hopefully we don't get any condensation up there. I am putting in an air exchanger to try to help that out as well. But the building is extremely tight. This is another view looking down the other way, just to give you an idea. Steve asked me yesterday, why I didn't put a second story on. This is why. We just we utilize the ability with the attic trusses to get a lot more room into it. So this is an example of the how the screws get sucked into the plastic. Normally you wouldn't use this type of a screw to adhere the mesh for the cultured stone for the scratch coat of the mortar, but we couldn't find any really that were readily available, and these were left over from the steel. They're 2.5 inches long. But what we found is once you hit that plastic again, it will draw that screw in fairly tightly. So if you were to run your hand from here over this screw head over to here, you wouldn't feel it, because this is indented right here. So it's not going to impede the mortar at all. And then we come up here. This is the most recent picture of the building that we have. And this is the scratch coat of the mortar that's on the building. Again, more cement, more concrete per se that we're utilizing. And the only decision left to be made is whether this gable right here gets done in the log siding to match the house across the street, or if we go with the precast logs. That's a nutshell right there. If anybody's got any questions, feel free to ask. I'm sure there's some things I probably forgot, but if you got any questions, let's hear them.
Feel free to use that Q&A button on your Zoom software panel, control panel, to type in a question. Just to reiterate, Doug, you're going to do the cultured stone on everywhere we see this scratch coat on top of the foam, correct?
Correct. Well, there's another note I'll give too here, which will be interesting, and maybe I'll give this an update. I think in the beginning, I don't know if I said it, I'll repeat it, but how Steve and Heather came to ask me to do this presentation is when I started it, I'm just playing. This is just a playground of concrete for me. I started posting all the different applications that we were doing on LinkedIn. I had some video feed. I was just describing what we were doing. If anybody's interested, if you go onto YouTube and go to the Premiere Concrete Admixtures site, you can see all these videos. But I'll continue to add to them, because one of the things I said earlier on, I'm a big believer in exposed aggregate. I like the way it looks. I like how it holds up. I like how blemishes that occur don't look like blemishes. But if you remember, going back to this slide here, this kind of has an exposed aggregate look. And I picked the colors because I've done some more exposed aggregate on my site, and this driveway is going to be exposed ag. So what should happen when these doors are open, whether you're on the inside looking out or the outside looking in, there should be a very close transition from the exterior to the interior. And I'm kind of hoping that we can pull that off. I think we will. The colors should match pretty closely.
Cool. Very cool. In regard to that floor, were there any special subgrade considerations to do that 80-foot by 48-foot jointless floor?
Actually, you know, I was kind of concerned about that, and I just deferred to the contractor. And to be honest with you, now the time will tell. You know, I don't know if there will be any additional settlement over time, and maybe a crack will occur. But they just threw about well, depending on the depths, I think it varied anywhere from 5, 6 inches to 8 inches. They just put stone in it, and it wasn't. Um, it was just gravel, and then they compacted it as best they could. It was pea stone, but they compacted it, and I was a little concerned about that. You know, I used to come, you know, when you talk about my experience in the testing industry and stuff, and compaction, I didn't know what to expect. But to be honest with you, I'm on the technical side. I tell people my expertise is plastic concrete, you know, subgrade preparation, things like that. You know, I just had to throw my hands up and defer to the guys that were doing it. So far, so good. But that was the only subgrade preparation we did, other than covering it and keeping it wet before the pour. There was actually a time when we poured that floor, or when we had it ready. I think there was a picture back here that right here, when we had everything laid out before they ran the hose on top of because below this vapor barrier is a 2-inch piece of closed cell foam. So I guess that's some special preparation on top of the stone that they compacted. There was 2-inch closed cell blue board on there, and then we put the vapor barrier. Well, the day that we were supposed to lay this hose out, it had snowed the day before, it had melted, and we had to shovel off about an inch and a half thick amount of ice before they could put that down. That was really the biggest wintertime hindrance that we got out of the whole deal. We got lucky with all the earthwork and stuff. They went right up to the day that they couldn't do it anymore, and we really didn't miss any opportunities. We got a lot to do. This building has to be finished by the end of May. I'm thinking we might get done by the end of April, but we got to put a well in over here. We got to put a septic tank in over here. Even though they do have a centralized sewer system, they have septic tanks for solid waste. Liquid waste goes into the pipes and goes out. Another concrete feature that's going to be done on this building is right here. We got to put a retaining wall that'll come out about this height. It's a little hard to see the contour of the ground, but we're going to have a retaining wall coming down to about here and then back down. That has to be done. That'll also be finished off with cultured stone. But you know, at the end of the day, when it's all said and done, I will have done what I always said I wanted to do. I built as much of a concrete house that I was comfortable with. Could have made the roof in tile or concrete tile and stuff like that, but I'm pretty happy with what I did.
Excellent. What would you do it the same way again? Anything you do different based on your experience so far?
The biggest thing I would have done different is that if you see back, I think there's one of these pictures. Here's a good one. I stopped doing the ICF right here. And the reason I did it, I kept changing my mind on how far to go out, because some guys, I talked to some people that had done ICF structures, and they said where they had big doors, it was just easier to go ahead and frame them in wood. And I didn't have the experience. And as I said, I mean, it was getting into winter. These guys, this was the last job they were willing to do. And then they called it a wraps, and the owner went to Florida after this job. So he was really nervous. And I didn't want to push him any further than I had already done, because we were really contemplating whether to take ICF all the way to here or not. In hindsight, I really wish I would have, because if I'd have done that, then this area right here wouldn't have been wood. I just would have got the additional benefits of the ICF. The window, we learned a couple lessons on putting that in, but if I was to change anything and redo it, I would redo that. I'd have made a couple changes on the floor, mainly the spacing of the trucks, etc. But that's hindsight. But we did continue to learn some stuff. The other thing I probably would have done is I probably would have put this snow guard up a little quicker. we got, as everybody knows, in this area of the world, we had quite a bit of snow. We had 2 feet on the ground at one time, and thank God it was only family members, but we took some headers coming out of the door once in a while because we didn't have the snow guard up.
Well, I just have one last question. Is that a fairly clay site? I noticed your excavations, they were pretty vertical excavations cuts.
Solid clay,
Okay.
solid clay,
All right.
all the way up. This right here, 10 foot down, solid clay.
Okay.
We have no sand in this part of Michigan.
Gotcha.
It's rough material to work with. Solid clay.
Okay. That's what I assumed based on the height of those and the steepness of those cuts to put that building into the hillside. So
Yeah. Yep.
Excellent. Well, I don't see any more questions. Feel free to type in if you do have them. But we want to thank Doug for his time this morning and your support over the years of MCA. We appreciate that, Doug, and you and your company. And just want to summarize. Let me see if I can get to my slideshow here. Big thanks to our sponsors as well as Doug and Premiere and Concure. We'll have handouts and the video of today's webinar posted on our website, and I'll get those certificates out. We are still continuing to post on social media with all of our awards projects throughout the next couple of weeks. We'll finish up with that. So hopefully people have seen those. We've been featuring those every Monday, Wednesday, and Friday with a new project. And all this information is accessible on our website. The annual conference page has links to all of these webinars, the videos, and the slide handouts from each of these. So that's a wrap. Thanks, Doug, and thanks everyone else for attending. Thanks to all of our speakers, our sponsor companies, and that is our workshop for this year. Hopefully everybody enjoyed it. Maybe we don't have to do this next year. We can do something in person, but some of this technology is here to stay. So some aspects of it will continue, and some things we hope to get back face to face. So thanks everyone. And thanks again, Doug.
You bet. Take care.
All right. Appreciate it.